As you'll realize, I'm Lukas, but the slide says Mariya. Mariya unfortunately couldn't come here, so I'll be presenting this on her behalf. And I'll be talking about the embed directive in Clang. First off, what is the embed directive? Because I think a lot of people are not familiar with it. It's basically a portable way to embed data, especially binary data, into your C and C++ code. And there was always solutions around to do that, but the embed directive is the first portable way to do it, so you can have that in different implementations, and it's not specific to one compiler or one linker. In addition, you get some parameters that you can specify. So for example, you have this limit parameter now that basically lets you decide how many of the data you want to import from a file. What's also nice about the embed directive is that similar to the include directive, it's basically resolves in the file system, so you only specify the name and the compiler will take care of resolving the file name. As a mental model of basically how this works is, so if you imagine we have some data file here that we want to embed, as a mental model what you can imagine is that it's basically taking the data from that and putting it as a list of integers, for example, in this case. And this works nice as a mental model, but it's not how it's implemented in Clang. And that's for a simple reason, and that's performance. And to illustrate why that is, we can compare two things here. So we have a solution that uses basically the embed directive and Clang's implementation. And then to compare and to see what the naive implementation would give you in terms of performance, we have a version where we take the XD tool, basically convert the binary data into actual hex literals and include that in our program, and then we can compare the compilation time and the memory usage of the two implementations. And if you look at the data here, you can see in blue the naive solution that basically takes all those data in that file, puts it into integer hex literals, and then puts it into the file. And you can see that depending on the amount of data that we want to include, our compilation time goes from like 5 seconds up to 25 seconds just because we include 20 megabytes of data. Compared to that, you can see that the Clang implementation of the embed directive does much better. So you can barely see the bar here, and it also doesn't increase as much as the naive implementation does. So how is this implemented? Why is it that fast? Essentially, okay, let's talk about the RAM. So also if you look at the RAM usage, you can see the Clang increases a bit with the more data you embed, but not as much as the naive solution does. So you can see the naive solution to include 20 megabytes of data in the source file, you get more than 2 gigabytes of RAM usage from your compiler. So that's definitely not ideal, and that's why we want to have this optimized implementation. In the simple case that we have an unsigned char array here, and we have an embed, we just get a single string literal in the AST, and that's basically how this is implemented. But using string literal for that isn't always possible, especially in the case that we have an array which is not unsigned char, we can't use the string literal here. So basically what the implementation then does, it uses this embed expression, which is basically an additional AST node in Clang, to express that we're embedding some data with the embed directive here. And so it's basically just a reference to the embedded data. It knows where it is, it knows how much it is, and represents that multiple bytes of data now as a single expression compared to if you would do it with the naive implementation, where you put a lot of bytes into a list and then you have one expression per item in that list. You now have a single expression that refers to multiple bytes of data. The embed expression can only appear inside of init list expressions, which will be relevant in a minute. And it's handled by the AST consumers similar to an array filler. So what happens in that case that we can't represent it as a string literal? We can also compare performance here. So we have the generic case, which uses the embed expression. In this case, we have an int array. And on the right-hand side, we have the optimized case where we get a string literal because we use an unsigned char array. So again, if you compare compilation time, it seems, okay, the generic case is somewhat slower than the string literal case. So that doesn't look too good on the first side. But if we add back our XSD, or basically our really naive implementation, you can see that it's not as bad. So we have the really optimized implementation in case you have an unsigned char here. We have the one with the embed directive here, and they're on this scale or on this y-axis, they're pretty close to each other. And then you have the naive implementation, which again takes a lot of time and also a lot of RAM. For RAM, you can also see with the generic case, the RAM usage increases a bit, but not as much as it does with the naive implementation. The important part that I wanted also to highlight here is that the embed expression can only appear inside of init list expressions. So that means if you use some embedded in the wild, as Mariya called it here, so you put it into some int here, you actually go back to this like integer literals, and that's obviously not great. For status of the embed directive in Clang, or it's available since Clang 19, it's supported in C23. In older modes, it's supported as a Clang extension. The embed directive is also on good track to be voted into the C++ 26 specification, so there's a good chance it will land there. As long as it hasn't gotten into the C++ specification, it's also supported as a Clang extension. There is some issues still to address in this implementation. Mariya has created a label for that, so if you want to follow the development or maybe even get involved into the development, you can just do that. And then there's an issue where Mariya describes some of the follow-up work that needs to be done. Yes, and that's it for me. If you have any questions, feel free to get in touch with me. I'm happy to connect you to Mariya so you can ask her questions. Yeah, thank you very much for your attention.